All right, we are coming to chapter 13. This is properties of solutions, and we are drawing some beakers right now, as you can see. And this is part 1, properties of solutions, by Mindy Bedrosian. I'm going to start a little out of order with the chapter. I'm going to talk about the 4 ways to express solution concentration. A reminder, 2 parts to a solution: the solute, that's the thing that gets dissolved, and solvent, the thing that does the dissolving. The most common expression of concentration is molarity, which is moles of solute per liters of solution. Remember, solution is both solute and solvent together. The next one is mass percent. This is mass of the solute divided by the mass of the solution times 100. Molality, which is moles of solution divided by moles of solute divided by kilograms solvent, only just the solvent. And mole fraction, which we've seen before, mole of solute divided by mole of solvent plus moles of solute, the total moles of the solution. So we're going to do an example and solve for all of those factors. 1.00 grams of ethanol is added to 100 grams of water with a final volume of 101 milliliters. So step 1, we are going to find the molarity. And if you want to pause and do that. And here's the answer. So change that grams of ethanol to moles of ethanol. And then you have liters. Well, you have change it from milliliters to liters. And that is molarity, moles per liter, which is designated as a capital M. There's the final answer. Hope you got it. Second part is you are going to find the mass percent. You want to pause? Otherwise, here's the answer. So 1.00 grams of the solute over the total, add them together, and you multiply by 100 because it's a percent, and it is 0.990%. Now you're going to find molality. You can pause at this point, otherwise the answer is coming. And here's the work for it. You need to have the moles of the solute over kilograms of solvent. So change it to kilograms. And that is moles per kilogram is noted as a lowercase m for molality. The last is you're going to find the mole fraction. And that will be the moles of the solute over the total moles. First, you need to change the grams of water to moles, which we will do right now. Then moles of the solute over the total, add them together. And work out the math and the final answer coming up. .00389 and no unit. So solution processes and energy. Just a reminder, everything involves changes in energy. So if we have a beaker with a solvent in it, delta H is endothermic because it requires energy to separate the intermolecular forces from the solvent particles from each other. That holds this together. You have to put in energy to separate those particles. In a beaker with the solute, you also have to separate those before they come together or when they come together. So this also requires energy input. This actually all occurs at once. But if we're looking at it separately, when you put them together, you have to separate those for them to fit together. However, for them to come together, that becomes exothermic. So here the molecules are mixing. So delta H for the mixing of the solvent and the solute is exothermic. Now the combination will determine whether it's overall exo or endothermic. For a hot pack, for example, will delta H solution be a negative or a positive number? Well, this will be a negative number because we are always looking at it from terms of the system itself. The system is losing energy. It's making you hot. For an ice pack that you can buy, the overall change in the energy is that it is endothermic. Energy is going into it. So this is a positive 26.4 kilojoules per mole. And this is the end of part 1.